Hi, good afternoon, everyone. So today we will be presenting our material analysis project on biodegradable and biorenewable packaging for use in food and beverage products. This presentation was composed and will be presented by Adrian Charles, Jadon Thomas, and myself, Karina Lachman. So to kick things off, we will firstly be looking at the product's function and its relation to design and material selection. Looking at the product function, the function of the product is centered around its ability to efficiently store and protect food and beverage products, reduce the reliance on fossil fuels, which would in turn reduce greenhouse gas emissions. In addition, the product functions to boost sustainability, allow diversification of feedstocks, as well as to lower production costs, making it beneficial in economy. Looking at the in-service and environmental conditions now, when this product is placed in service, it must be able to store hot food and beverages without degradation. It must also be able to withstand everyday stresses experienced by food and beverage packaging, and when it is placed under environmental conditions, it is biodegradable. Alright, so now we are going to consider the design features of the product, which encompasses its antimicrobial properties, mechanical, optical, thermal, eco-friendly, and barrier properties. Essentially, the product should be designed with a maximum strain and level of toughness so as to sustain a good mechanical integrity. A large surface area is also advantageous in this case of food and beverage packaging. It is important for it to be designed with little to no toxicity so that it would support its functions to safely store products. The packaging should also be designed with enhanced flexibility, durability, and heat resistance, which would in turn support its good mechanical properties. So now we're going to touch a little on the material that actually makes up this biodegradable packaging, and this material we looked at is PLA, polylactic acid. So PLA is a high molecular weight semi-crystalline thermoplastic. It is created from the fermentation of cornstarch, sugarcane, or sugar beets, and they are biodegradable and compostable alternatives to petroleum-based plastics since it is manufactured with non-toxic resources. So as we mentioned previously, PLA having a high molecular weight, which we can clearly see from the chain length of its chemical structure. Because of this, its melting and boiling points, glass transition temperatures, impact resistance, strength, and toughness are all considered in its material selection. So looking at the product function and its relation to design and material selection, we can conclusively say that the designing of the product is influenced by its functions, and since its biodegradable packaging are seen as green alternative, it should be designed to uphold sustainability in nature, of course, as well as having exemplary physical and mechanical properties to ensure its suitability to work as an efficient bioplastic.
Hi guys, my name is Adrian. So, how is polylactic acid obtained? Polylactic acid is obtained from the addition and condensation polymerization of its monomer, lactic acid, which is extracted from the sugars in plants, corn in particular. The reason why both forms of polymerization needs to occur is because condensation polymerization produces a molecule of water which prevents the monomers from sticking together. This causes multiple short-chain polymers to be formed instead of one long-chain polymer. So on your screen now you should see a detailed chemical structure of polylactic acid, PLA. On your screen now you should see the different properties of polylactic acid with their respective values, all of which should be examined later on in the presentation. On analysis of the lifespan of polylactic acid, from how it's produced to how it's decomposed, it should function fairly well as a replacement to conventional plastic packaging. It is synthesized from renewable resources and is generally healthier for the environment. There are also some issues that may arise from the usage of polylactic acid for packaging, which will be discussed further. I'll now hand you over to Jadon.
Good morning. My name is Jadon, and I will be presenting the material performance / potential failure of polylactic acid plastics. Why use PLA? Well, PLA has good durability, high strength, it is biodegradable, it is transparent and glossy, which would make for attractive packaging, it is non-toxic and has antibacterial properties, and also it generates 68% fewer greenhouse gas emissions than conventional plastics. So what are the disadvantages of PLA plastics? Well, it is expensive and has a poor chemical resistance which will lead to degradation by acidic foods and beverages. It is also brittle and has a high gas and moisture permeability which will lead to faster spoilage of food, and it also takes long to compost. What are the possible alternatives to PLA plastics? Despite the challenges of PLA plastics, it is still the most widely used bioplastics since its faults can be corrected through PLA composites. These composites consist of natural fillers which make the plastic cheaper and also lead to greater physical and chemical properties. I'll now pass on to Adrian.
I will now be examining the implication of bioplastic production. One of the major downsides in this is that of energy consumption. It requires a lot of energy and resources to produce bioplastics as well as to decompose bioplastics when compared to other conventional plastics. Another issue or another downside is that there might be a competition for food. If bioplastics are integrated on a large scale, since it is essentially made from plants, this may cause a competition for food to feed the mass population, and as a result of this can lead to famine and, a worst case scenario, death. Another issue or downside is that pollutants, even though it is not greenhouse gas emissions, other pollutants may be released, such as phosphates and nitrates, because fertilizers may have been used in producing the crops, which may then transfer over to the plastics themselves. To the answer to the question posed above, is there a future in the large-scale operation? Yes, there is a future, but some adjustments in the bioplastic process needs to be made. Recommendations for the future of the product can be seen in the next slide. These include monocropping. Monocropping is the planting of one particular crop among a large area of land. This may solve the issue of food competition. You can also source energy from renewable sources, which may solve the dilemma with energy consumption, and you can practice reducing, and recycling with your products, which will eventually decrease the demand of bioplastic production and will mitigate the negative effects that comes with this process. So, in conclusion, the potential for bioplastics to replace conventional plastics is very promising, but there are pros and cons to this which must be addressed and solved.